Hello, everyone. Good afternoon. I know there's still some people that are joining in. We're going to give everybody just one more minute to log in. But in the meantime, we can go through some introductory items and housekeeping while we're waiting. So first of all, let me welcome you all and thank you for joining us today for our Connect webinar. The title of today's session is Leveraging Private LTE Networks for Direct Transfer Trip DTT systems. This module is part of our protection series, and we are having two presenters today, and I'll be introducing you to them later. My name is Tracy Jennings. I'm the marketing coordinator for the RFL products under Hubbell Power Systems, and I'll be your host for today's webinar. Next slide, please, Brian. So before we get started, I just wanted to go through a little housekeeping about the webinar and then a summary of what Connect is and how you will benefit. And then I'm going to introduce today's presenters. So just so everyone knows, we're recording this session and I'll make the video available. I'll put it on the RFL website in the Connect archive section within the next few days. So hopefully by the end of the week, so be on the lookout for that. At the end of the session, I'm going to send an email out to everyone who registered with a PDF of the slides. The email will also include a link to a white paper on this topic. It was co-authored with our presenters today, Brian and Jason. So you'll be able to download that directly from the link in the email on the RFL website. And then if any questions that you have as we're going through the material, please feel free to enter them in the Q&A box. Use the chat for anything else. Just if you can, keep your Q&A box. So now I want to go ahead and take a moment just to learn a little bit more about our Connect Learning Center for the power utilities. The center was developed over 20 years ago now, and it was developed in order for us to share information on the hot topics of our industry, which about 10 years ago was cybersecurity. You guys will probably remember the NERC standards that were rolling out. So that was the primary focus, a way to share information about a particular topic. But over time, we've continued to provide webinars on many other topics in the substation communication and protection areas as well. And if you have any suggestions for any other topics that you'd like to see us present on, please jot down my email address. It's shown there on the bottom of the slide, and I'll be happy to take a look at that and think about future presentations. We are continuing to provide our webinars on a complimentary basis because we do believe that they add value and they help keep us connected to our valued customers and associates. If you have a chance, please visit the RFL website. You can learn more about Connect and you can download other archive sections on other topics, including cybersecurity. And there's a really nice series of protection, power line, carrier 101, PLC 101. There's some networking webinars that we've done several years ago. So there's a lot of information there. And we welcome you to the website to take a look at that. Okay, next slide, please, Brian. So now I'd like to introduce to you our two presenters for today. We have, as I mentioned, co-presenters, and this material that they're providing to us today has been presented in various other forms over the past year or so. And we're very happy to have them today at our Connect session. So first up is my friend and colleague, Mr. Brian Dobb. Brian is the product manager for RFL Protection Products. He has his BS in Information Technology and MS in Engineering Management. He's a member of IEEE. He now has over 20 years experience in the power utility industry. He's concentrated his efforts mostly on the power utility communications for protection applications. And as I mentioned, he's responsible for RFL Protection product line, which includes power line carrier, audio, tone, and digital teleprotection, as well as line protection relays. I invite you guys to visit the RFL website. You can learn more about the solutions RFL products offer. There's a very nice solutions guide there that will really walk you through a lot of the products and how they can suit your applications. Next up is our new friend and colleague, Jason Mills, PE. He is the solutions engineer with Anterix. He has his MS in power engineering and BS in electrical engineering. And Jason has over 15 years experience in the power industry, focused in the distribution, transmission, and nuclear generation sides of the industry. He has experience working in areas, as you can see here, smart grid automation, OSI implementation, DER capacity planning, and nuclear risk management. And Anterix is a USA leader in communications technology advancement, providing leadership to utilities to understand their needs for advanced connectivity, data collection, and smart infrastructure. Thank you both, Brian and Jason, for your time today. We look forward to hearing your presentation. And now I will turn the webinar over to Brian.
Thank you, Tracy, for the introduction, and welcome everybody. Thank you for joining us today and spending some time and what we have to say about private LTE networks and direct transfer trip. So our purpose of this webinar is really to share our experience with evaluating private LTE networks for direct transfer trip systems. And so we'll introduce the direct transfer trip systems for distributed generation applications first in our agenda, and then we'll do a brief overview of private LTE and cover our testing methodology. And then we have 2 test cases that we want to present the results of, and then just finally close that out with some conclusion and some final thoughts. So we'll start off with direct transfer trip and the application that we are covering as part of this webinar, and also part of the paper that we had written on this topic is really around anti-islanding of distributed generation. And so we'll cover that and talk about DTT for that application. So to start off, a power system, what is a power system island? Well, a power system island occurs when distributed generation, which is producing power and exporting that to the grid, becomes isolated from the utility substation and continues to supply power to, and this is referred to as a power system island. There's 2 types of islanding, what's called intentional islanding or unintentional islanding. Intentional islanding would be, something like a microgrid, where it can operate independent from the grid. And you have unintentional islanding, where obviously this is not intended situation, but where the generation can become isolated and continue to backfeed power into this island, not connected to the substation, utility substation. And specifically, unintentional islands can be a risk to personnel safety, power quality, also equipment damage. And so we have standards like IEEE 1547, which will, if you look at that standard, that recommends that islands be removed within 2 seconds. So direct transfer trip is one of the most common methods of communication assisted methods used for anti-islanding protection. And one of the main benefits of direct transfer trip is that you can eliminate what's called a non-detection zone that may be found in local type anti-islanding methods. So with a direct transfer trip system, you don't have a non-detection zone as long as you have a good communications channel. And another benefit is to having utility control of the interconnection. So the utility can directly control the interconnection of the distributed generation. And then a side benefit too is that with direct transfer trip, those local frequency and voltage elements that may be otherwise used to try to determine an island condition, those can be set less sensitive, and then also help some and prevent false operation. For direct transfer trip, this is a pretty straightforward application. Uses some sort of communication network. This could be a wired system. It could be a wireless system. And the goal, of course, is to send a trip signal from the utility station to the generator and prevent that generator from backfeeding power. This could be by opening the point of common coupling, for example, between the generator and the utility grid or distribution circuit, for example. It also could be initiated from other devices like a recloser. So if a recloser operates and locks out, that recloser can also be a source of islanding, so that can send a transfer trip signal to the generator as well. And we're showing that here in the bottom right image, where you may have multiple devices, multiple reclosers, a utility breaker that is being used to initiate a transfer trip signal to be received by the DTT receiver at the generator. The communications technology for direct transfer trip systems has evolved and is still evolving. You may be familiar with legacy type communications that were very common. These would have been audio tone circuits or phone lines leased from telco companies, could also have been T1 lines. A lot of those are not available anymore. In fact, the telcos at this point in many places are starting to sunset those and basically turn them off. So if you still do have one of these phone lines or T1 lines, a lot of times there's reliability concerns with these. Also, they tend to be very expensive, monthly recurring costs. Another alternative too is of course direct fiber, and this is a good alternative in performance, but it can cost tens of thousands of dollars per mile, and this really quickly becomes very expensive over distance, and really having the distributed generation pay for that can be a problem for these projects. So this kind of has led to exploration into public cellular LTE networks. Of course, public cellular is widely available across the country. Telco companies, for telco companies, this is a major focus of their business, and you have good coverage here, although you have a lack of control of the coverage, of course, because with public cellular, you can't control where the telco company is going to install a tower. May also, because this is public infrastructure, performance may be experienced as well. Different times when there's different usage of the public cellular network. And so this has also led us to explore the use of public LTE. And I will let Jason introduce the public LTE.
Or thanks, Brian. I think you meant the private. So we're going to talk about kind of
I'm sorry, private LTE. You're right.
So kind of how Brian's been touching on, and I saw someone threw something in the chat. So if you do have any questions, please throw them in the Q&A or in the chat on Tracy in the Q&A bubble, and then we can address the questions at the end and come back. So talking about, right, Brian kind of touched on legacy technologies and transition to public, and what we've been seeing is a transition to private LTE, and what that has enabled. We've seen over the last couple of years, over 10 major IOUs have transitioned their comm system to private LTE. Demand, being able to manipulate and monitor all their equipment and control what data they pull back and what data they don't want, given whatever operational situations are occurring, right? What they're getting out of that is improved reliability, being able to see point-to-point every single piece of equipment that's out in the field, whether it's a DER site or whether it's a SCADA point coming from a recloser. They're able to control and see all those different points and be able to operationally make decisions. One thing specific is around deterministic latency, and that's something we'll touch on, and that's a key factor that kind of is a little bit different than the public LTE, right? Being able to utilize private LTE and using its functions, you're able to have the same consistent latency to all your devices 24/7, 365, and you're able to manipulate that and get the latency down or up based on your specific needs. Next slide, Brian. Slide again. Okay, so what is private LTE, right? I think we're all very familiar with what public LTE looks like and fiber, right? But private LTE is a newer phenomenon that's been hitting the utility industry over the last 5 to 7 years, right? So that's why, back in the day when we were doing different things, this wasn't an option. So this option became more available in the last 3 to 5 years, and utilities throughout the U.S. have been investing and building their own private LTE systems. What allows them to do that is it becomes a utility-owned system, utility-operated, removing reliance on any third-party carrier or any third-party organization. Where it's useful is electric utilities, generation facilities, right? Your reclosers. Those are all those pieces that are all going to connect to your own utility-owned private LTE network. What makes it unique is, right, the utility owns it as if it's their own substation, their own comms. The utility has their own towers. The utility has their own core. They own all the pieces end to end, including the data coming back from a recloser or whatever end device that's at your DER site. That only comes through your utility network in full circle. So encapsulation, all that data never goes to a third party. So there's limits, security threats, limits outside intruders being able to get that data, de-encrypt that data, use that data for other issues. All right, next slide, Brian. So on the next slide, we're going to kind of talk about what we did in the actual testing, kind of drive through where we landed on the test case. Next slide, Brian. So this is what we overall did for the test system overview. What we took is an RFL substation direct transfer strip device, the GARD 8000, and we put it on 2 different locations to initiate what a field situation would be like. So on the left would be your utility substation, and on the right would be your solar generation plant, right? Assuming that those 2 devices are far enough a distance away that they're talking to 2 different towers, but connected in the back end to the core. Right, so we tried to simulate, hey, if I have a substation and I need to send a signal, what would that look like? In addition to that test, we simulated background data. So what we did is we didn't just wirelessly connect these devices and only send direct transfer trip. We also added noise generators or data generators on both sides to simulate what a common flow of data and packet capture would look like on both ends, so that we could see what a real life scenario would look like. So this was all done in our lab, and be able to simulate, a faraway substation and a DER site being connected and sending direct transfer trip signals to each other. Next slide. And then I think Brian's going to go through kind of the 61850 kind of communications here.
Yeah. So this is a little bit more detail about the equipment used in this test setup. So we're using the RFL GARD 8000 device to generate a 61850 goose message. This is a layer 2 goose message, and we utilized a to relate this layer 2 goose traffic and send that over the private LTE cellular network. In addition to that, we also utilized 256-bit IPsec encryption. So there's a VPN, encrypted VPN tunnel with generic routing encapsulation, and that is carrying the layer 2 goose traffic end to end. So a little bit about the performance testing methodology that we went through to evaluate the performance of the private LTE system. So we have these GARD 8000 that are sending the goose traffic between each other over the cellular network. And what we did to characterize the performance was send a transfer trip from the A unit on the left, send a transfer trip signal every 250 milliseconds, and do that repeatedly over a period of time, sending thousands of these trip messages. And then at the remote end, we loop back that DTT signal and send it back to the initiator. So it's a round trip type test. And at the initiator side, we can measure the time delay between the sending the input and receiving that DTT output back at the initiator device, and measuring the time delay between the two, and then characterizing them or categorizing them into different time delay buckets. So this is a two-way test, round trip, and so roughly 1/2 of that time would be representative of a one-way latency that you would see in the field sending from the substation to the generator. So the times that we show here are going to be mostly round trip times, and so just keep that in mind, that 1/2 of that time would be representative of a real world scenario. So our first test case, I'll introduce that and go through some of the results. The first test case, the goal was really to evaluate the private LTE and compare that to public carrier testing that we did as well, and evaluate these for reliability and latency using that methodology that I covered on the previous slide. These are the different time buckets that we use to capture the received trips. So for the private LTE, we had a 90 millisecond, 110 millisecond, and 125 millisecond time bucket. And then for public, we had 100, 120, 150. The reason for that was because the latencies are a little bit different between the two systems, and we wanted to be able to try to characterize the performance more accurately. So setting the time buckets a little different helped in that regard. The private LTE system being a little bit faster than the public system, and we'll see that on the next slide in the results. Also note, like Jason said earlier, we do have background traffic on the network as well. So the private LTE system, in addition to the direct transfer trip communications, was partially loaded with some additional background data, really to simulate some, a real world scenario as best we can in a lab environment. These are the results for test case 1, and the first takeaway that I would say is that you'll notice that for both networks, private and public LTE, none of the transfer trip messages were dropped. So they were all received round trip. None of those were dropped. But you will notice that the latencies are a little bit different, and the percentage for each of the time buckets is going to be a little bit different. So with the public LTE, you can see that we received 99.9% of the trip signals in 150 milliseconds round trip. Whereas on the private LTE, we had 100% within 110 milliseconds. So there's a roughly a 40 millisecond difference between the two there. The other thing I would point out too is that in comparison to the public network, the private LTE network is a little bit more consistent. There's less variation in the latency. So you can see there's roughly 5% of the traffic fell into somewhere between 90 milliseconds and 110 milliseconds, whereas roughly 5%, a little bit more than 5% on the 0.1% on the public network that is not accounted for here. That was just longer than milliseconds happen to exceed that timer. So, I would say in general, worst case, we have here 150 milliseconds round trip. That's, typically suitable for these distributed generation anti-islanding type applications. And we see we had good performance. And the variation in timing is a little bit better on the private LTE. It's more consistent. And so we explored that a bit in the next test case. But I would say, kind of in conclusion, both systems performed pretty well. Private LTE was a little bit faster and a little bit less variability. But in terms of this application, I think both of them performed pretty well. Worst case, we had a one-way time of 75 milliseconds, 99.9% of the time for the public LTE network. I'll now pass it over to Jason to cover test case number 2.
Okay, thanks, Brian. So test case number 2 is a little bit different than the first one. What we are testing on the second test case is, how does a PLTE system perform differently under partially loaded network versus something heavily loaded, right? And when I talk about heavily loaded, it's a congestion level event, right? If there's an earthquake, a heavy storm in the system, everybody's trying to communicate at the same time. What does that communications network look like? And how does it perform compared to, right, what you guys have experienced during storms, during whatever events have occurred in your specific utilities? You've seen loss of connectivity, right? And with a private LTE, you can control that aspect, and we're going to kind of talk about that. So we're going to use the same sort of time buckets that Brian talked about, but really comparing on the private side, how do we see performance change from a low congestion network to a high congestion network utilizing QoS? So the next slide, we'll talk about this specific function of private LTE and every private system is QoS, also called quality of service. And for what that means is, all your data is coming through, every minute, every day, but a data event occurs, right? So you are able to provide a QoS or a prioritization during that event. So if a storm flag goes up, right, for example, you're able to prioritize certain functions and certain data paths to come into your system at 100% reliability and maybe downgrade some of the less important data. For example, right, a storm comes through, your storm flag comes up, you want to get all your recloser data, DA data from all your points at 100% reliability. And you're able to shape your traffic to make sure that that is first high reliability and you get your lowest latency on all. At that same AMI billing data, you don't need that information congesting the system, congesting the pipe. So you deprioritize that data. And that data sits in a queue. It'll come back after your event, right? The data doesn't disappear, but it just sits in and gets deprioritized. So you, during that event, can control what information I get, how fast I'm getting it during any of those events. So think of it as ranking, right? 1, 2, 3, 4, 5, 6, 7, 8. You're able to get your priority 1 first, and it, the system maintains that data 100%, and it gives it the low latency. But priority 8 becomes the last thing in the queue. But you're able to shape that data and shape that data path as you, the utility, the end user, deems fit. All right, next slide, Brian. So that's what we try to push out as this test case number 2, right? What a partially loaded system would look like, and then a heavily loaded system, see how those metrics would be impacted. So what we had is the same 90, 110, 125 milliseconds buckets for that full round trip data that Brian talked about, right? So round trip is 90 milliseconds, so one-way signal is about 45 milliseconds. I think Brian explained that a little bit. So in the top chart, we talk about partially loaded. So this is the same data that we had in the test case 1. But what we wanted to see is if we overloaded the communications network during a significant event, how that direct transfer trip data would be, if it's prioritized as level 1 priority, what that performance would look like. And what we saw is there was a minimal dip in performance. So during a heavily loaded scenario of a significant event, we were still able to capture 100% of the direct transfer trip signals. And as you can see in the latency, you were able to still capture, instead of in the partially loaded system being at 100% data capture at 110 milliseconds, at 125 milliseconds, you would notify or regain 100% data capture. But you can see, if you compare the 110 milliseconds in the two charts, you're only losing 0.003% of all data capture was impacted due to this heavily loaded event. So this is a primary function of Private LTE, allowing you to shape and prioritize your mission critical data during mission critical events, right? So during this event, right, when the system is completely overloaded, you're only able to see a minute difference of 0.003% of all packets slowing down or not getting to your head in the same speed that it was doing in a normal operating scenario. And that 0.003%, you're able to capture that in the next 15 milliseconds. So that's an important piece to understand, to capture as we're losing data, as we're trying to get data from sensors, as we're trying to get data from meters, right? As you know, if there's outages occurring and rolling outages and nesting outages, this becomes the funnel that you guys can manipulate and create and make sure that you get the data during these operational events that is critical and important. Next slide, Brian. So in summary, right, a PLT allows you to give priority and give criticality to your mission critical data points and devices that you guys prioritize as critically important in the protection field, right? Protection applications are extremely critical to how the utility does fault location, does DER tripping, right? All those things are very critical, mission critical points. And with PLTE, a private system, you're able to control that and make sure you never lose any reliability or dependability on any of those connection points, right? But one piece also is allows you to have a funnel to pull as much data as you want back from those points, right? We don't always have to do SCADA points or a subset of DMP3 points, right? We can pull synchrophaser data back from those reclosers, those SELs. We can bring all your DMP3 points, any of those things that controller is able. PLT allows you to create your own size funnel to those pieces of equipment to bring as much data as you want to make operational decisions. And the piece that enables that is quality of service, allowing you to shape the funnel to every device as you deem fit automatically, given, right, as you set up your system. This is all an automatic system that you prioritize when you set up and build your system. And then therefore, right, your reclosers and all this data transfer occurs automatically. So your operators don't have to do any of this configuration, right? This is all built into your communications network, further enabling your ability to make timely decisions in real time. Next slide, Brian. Brian, were you the conclusion slide or was this me?
That was you.
Okay, all right. In conclusion, don't want to step on your toes. Thanks, Brian. Reliable communication is important for direct transfer trip, but not just direct transfer trip, really any protection application, right? And that's why a lot of protection applications have been reliant on fiber or microwave, because dependability and reliability is key, right? But what we've shown and been able to show with different customers is, private LTE and having your private wireless system can be as equally reliable as your fiber and your hardwire connections and more cost effective, right? We didn't dive into the costs, right? But this allows you guys to enable and deploy devices within your territory without any incremental cost. Any new DER sites, any new reclosers, all those pieces wouldn't come with any additional cost, right? Those are additional infrastructure. You won't have O&M associated with those pieces, but you have high level performance that you're not getting currently today. So in conclusion, right, we're going to be able to outperform, right? The technology isn't new. This is the same technology that AT&T and Verizon is using. It's LTE, what lives in your phone today, right? It's the same technology. It's just privatizing it so that the utility owns it, and the utility is not sharing it with kids doing TikTok or other vendors doing different testing in the area, right? It's not a shared network anymore. Private networks become your utility-owned network on the same technology that you're using every day in your phones and that AT&T and Verizon. It just becomes privatized for utilities to use in their smart grid advancements and maintain reliability and dependability of their different use cases. I'll leave that open for Brian if he's got any finishing thoughts, and then we'll open up for Q&A.
Yeah, so we can open up for Q&A. I think there was, don't see anything in the Q&A. I don't know if Tracy, you see anything, but I did see a
do.
question.
I do. There's two questions. So the
Oh, okay.
first question that came in, it went into chat, but then he reposted it.
Okay, got it.
And Brian, I think these are probably both going to be for you, and somebody just posted a new one. But the first question that came in was, how about microwave?
Yeah, so microwave is something that we have, some experience with in certain cases. So microwave is an option for communications between stations. I mean, it's used pretty heavily between substations. I have encountered maybe one or two places where it's been used between like a third-party generator. But yeah, that's a viable option. A lot of the microwave systems now are packet based. And so that's, same goose message that we talked about, can be carried over a microwave system. If it's an older type microwave system, T1 type communication usually is supported by those older microwave systems. So those are two methods that our platform supports that could be used with microwave.
Thank you, Brian. Then the next question is definitely for you, Brian. Do LTE or PLTE have an established standard of channel communications such that RFL products work seamlessly regardless of LTE or PLTE?
Yeah, so I'm not. I think I'm going to answer the question. If not, let us know. But the testing that we did for public and private LTE used the same communications system, same protocols, same devices. Just the only difference was that the cell routers in the private LTE case were configured to operate over the private LTE spectrum versus the public. So same communication protocols can seamlessly work over private LTE and LTE. I would add additionally too that a lot of our customers that are using or looking at using cellular networks or private cellular networks are looking at also doing simultaneous communications over two networks. So, and that could either be done through an active type router, or that could be done through two parallel routers. And, we support the parallel redundancy protocol, and where we can send the same traffic simultaneously over two networks. And as long as one of those networks is functional at the time, you have no loss of communication, no switching time, anything like that.
Okay, a few more questions coming in. Thank you, Brian. I think, Brian, this is probably for you too. Are you using routable Goose or a VLAN or VPN type service with layer 2 Goose?
Yeah, this is a VPN GRE, VPN/GRE tunnel. It was encrypted with 256-bit encryption, and that's carrying the layer 2 Goose. It's not routable Goose.
Okay, we got a thumbs up on that. The next question was, are there any cybersecurity network hacking concerns?
I mean, I think that's,
I can dive into that, right? So I guess the question is around about the wireless network hacking concerns.
I would assume so.
It just says, are there any cybersecurity network hacking concerns?
So I would say what we've talked about, and when the 10 utilities who have already made the move to private LTE, this is how they mitigate their cybersecurity risks and the network concerns, right? So this is one of their methods to improve their cybersecurity on their wireless, right? Because of the encryption needed on the edge, right? By bringing all your end devices and all your gateways in-house, you're able to manage and put layers of cybersecurity that you deem fit on your wireless system, right? So it takes that control, and you're able to work with different companies like OneLayer or different Palo Alto, different security firewall manufacturers that fit your specific needs, and you're able to build that to add additional security. So I would say most utilities who have made this move are making this move to improve their cybersecurity and to get away from the sharing of AT&T and Verizon. And moving away from the outages, right? So when Verizon, AT&T have hacks and outages, right, that affects all the consumer bases and all the connectivity, right? So having a private system allows you to create an island or create space between a gap between your devices and all the rest of the world.
Okay, very nice. Give us a thumbs up if you can on the reaction. If we covered that all for you. The next question was, can we use free wave radio for DTT?
I'm not familiar with free wave radio, although I will say that we have utilized other RF communications, packet-based, licensed, unlicensed communication networks for direct transfer trip. So I hope that answers that question, but I'm not specifically familiar with free wave.
The next question was, will there be any difference in latency between T1, E-line, LTE, PLTE? Understand it depends on Verizon or communications company.
Yes, there will be a difference. So with the LTE, private LTE, you're kind of around the 50 millisecond area, with some variation on the public network. And I think we demonstrated that in the results on the two test cases. With E-line and a T1, these being wired type systems, the latency is going to be less. So we've seen latencies on T1 and E-line systems, can be under 10 milliseconds is possible. Really depends on how the circuit is run, how many hops you're going through, especially if it's a leased type network. But certainly under 10 milliseconds is possible with those.
Thank you, Brian. I don't see any other questions. Does anybody have any other questions? We'll just wait another minute or so, just in case. Looks like a new one just popped in. And I don't know why you guys are not. Brian, this is for you. Brian is a genius. Thank you so much. And no, it wasn't from your siblings.
I don't know about that, but thank you.
He is very, very smart. I've worked with him for many years. Very knowledgeable on this topic. Any other questions from anybody? These are good questions. Thank you very much, everybody, for participating with us. And I know Jason and Brian really appreciate the feedback and the questions. So
Yeah, absolutely. Thank you.
we have a new question. Yes, the question was, would you please send the presentation? So yes, I will be sending out this afternoon a PDF of the presentation. And in case you weren't logged in the beginning, there will be a link to, there's a white paper that Brian and Jason co-authored on this topic. I'm going to give you the link to use from the RFL website, and you can download it there. I believe it's already on the website. It's in the technical paper section. And I'm pretty sure Anterix has it also on their website. So you can grab it there too. And somebody put in chat, thank you, good presentation. It was, they did a great job. So thank you guys. All right.
There's also a question about certificate of attendance.
Certificate of attendance. I'm not really sure what that is. I think you can probably evidence that you were here, but if you mean like the report out, I can just send me in the chat specifically what you're looking for. I've never been asked for that, so I don't know what it is. And also, if you weren't here in the beginning, when I was going through the intro, the recorded session will also be uploaded on the RFL website. I'm going to share a link also with Jason so they can post it on the Anterix website as well. You guys should feel free to check out the Anterix website too. Any other questions or comments? Okay, the only thing is for privacy, I don't know that I want to share the whole report. Mazamel, so let's take an offline conversation and I'll see if I can get you something, but you should be able to evidence that you were at the webinar from your login. All right, everybody, with that, I think I'm going to end the event and the recording. Thank you. Oh, continuous professional development. There, we do not offer that with these webinars. There are no professional development hours available for this. All right. Everybody's saying great job. I'm sorry you guys can't see the comments and the posts and stuff, but everybody's saying great job and thank you. All right. Ending the event. Have a great rest of your day. We hope to see you at the next Connect webinar. We're hoping to get Brian to do another one for us in the fall. So we'll reach out to you then.
Thank you. Take care, everybody.
Thank you.